Continuing on here, chapter 17, I think. So we were talking about electrochemistry, and we were talking about sort of galvanic cells, I think, for sure. And remember, with galvanic cells, we have our anode compartment where oxidation occurs. So electrons go off that way. And it goes off to the other side where we have our cathode and reduction occurs. We have a salt bridge that typically bridges both of our compartments here in our galvanic cell. We could calculate our E of our cell by using the SRP values we could find in a table, standard reduction potential values. We take E of our cathode minus E of our anode. Remember, as we talked about a lot of times up to this point, the fraction here is to change the sign for you. Sign of the anode one. Again, because in that SRP, they're all written as reduction reaction. And since the anode side is an oxidation reaction, technically reverse that reaction. But if you just want to use the values out of the table without having to worry about doing that, keep the subtraction there. If you want to change the sign of the anode, then you should add them together. So again, don't do both of those things. We also talked about the relationship between delta G and the of the cell, and here F is Faraday's constant. E of a cell is obviously what we have above, and again here a positive voltage there will turn our delta G into a negative in a spontaneous reaction. So positive voltage is good. Negative voltage, on the other hand, will do the opposite. Negative will turn our delta G into a positive, and it will be a non-spontaneous reaction that occurs. We also saw the Nernst equation. Natural log of Q. I'll get that there. Natural log of Q. And again, this is for non-standard conditions. So non-standard conditions. Remember, standard conditions is 1 atmosphere or 1 concentration. So if they are not those things, then you would want to use the Nernst equation. We also saw that E of the cell is going to equal to RT-NF natural log of K, the relationship between Fourier constant as well. And you can kind of get that from the above equation. Remember that all those things should sort of agree with each other. So if you have a positive cell voltage, you should probably have a negative G, and a negative G and a positive cell voltage should probably give you a big value or a large value of K over 1 at least. And opposite is true. If you have a negative cell voltage, that would give you a positive delta G, which means non-spontaneous, and you expect a smaller value of K. Any questions on any of that there? All right, so I think we left off here. So we're just going to talk about batteries a little bit here. And again, basically, you don't need to know any specific reactions for any specific batteries or anything like that. Just to know, again, how similar are differences, similarities between a battery and a traditional galvanic cell. So a battery is, again, a galvanic cell or a series of galvanic cells used to provide direct current. They're self-contained, do not have a salt bridge, obviously. It would be a little messy. Try to put that in your battery compartment, I suppose. So here's one type of battery. This is sometimes referred to as a dry cell. Looks like Duracell as well. And in this type of battery here, we have the anode, which is our can, and that's our zinc sort of container there. And we have our cathode, which is this sort of rod in between, immersed in an electrolyte solution. And again, there is, just like in a traditional galvanic cell, sort of a positive side and negative side. And just like in a galvanic cell, right, electrons should be traveling towards the positive side. And obviously, there's usually wire, which then in your compartment, that those electrons go out and do some type of work, using like Gibbs free energy there to do some type of work as you're kind of doing this. Again, usually we have inside some type of strong electrolyte kind of almost acting like a salt bridge, kind of keeping everything flowing. This type of battery, regardless of the size, will give out 1.5 volts, regardless if it's like AAA, AA, C, or D. And here, if we look at sort of the equations here, we can see the zinc going from zero oxidation state to +2. So once again, becoming more positive and go through oxidation. On our other side here, we do see the reduction that is happening on our Mn here, for example. It is +4 on this side, and over here +3. So becoming more negative in that case as it goes through here. And again, we get our overall reaction that is taking place. Another type of battery is a mercury battery. It's used a lot in medical and electronic industry. It's a little bit more expensive than a dry cell. Also contains a similar type of setup a little bit. It's got our anode, which again is sort of a zinc can. It's also got our cathode here, which is some steel, and a very strongly alkaline sort of solution here. And alkaline means basic, so something like KOH there, which is a strong base, also a strong electrolyte. Again, the idea there is to keep everything kind of flowing and the right sort of overall charge happening here. Now, one of the things about this is there's no change in the electrolyte composition during operation, which is really good, again, for sort of longevity of the battery, and also, again, just on keeping things flowing. This gives a little smaller voltage, 1.35. And once again, we got our zinc going from 0 to +2. Here's our mercury going from +2 to 0, in this case, getting reduced here. And one of the things that is kind of important in this one, and really one of the things that's kind of good for a battery, is having sort of solids there, the overall reaction, which you can't really see there on the screen, but if you go down, you end up with a lot of solids in the overall reaction. And that's really good for longevity, also really good for sort of recharging and those type of situations. Lead storage battery, which is used in cars, and traditional sort of lead storage battery has 6 cells basically hooked together. Each one gives off about 2 volts, which is your 12-volt car battery typically that you put in there. And again, that's enough to get you started, to start the ignition circuit and other electrical systems in your car, except when you're running late and you try to turn it on, it doesn't want to start. It is rechargeable, which means, again, kind of reversing that normal electrochemical reaction by applying an external voltage. Also, we don't drain out our batteries because, we got things like alternators and stuff like that in our cars as well. Good battery health. You could check your battery. 1.2 grams per milliliter is the electrolyte sort of solution. Again, depending if you live in a kind of cold area or even warm area, the electrolyte can get very viscous, especially in cold areas. Here's a cross section of our battery here. And again, we have our cathode and positive, negatively. Maybe your battery in your engine, battery, but it may be actually be in there. At least these guys jump in case you ever need to. And again, they're usually sealed. So we have our battery acid in there. In this case, sulfuric acid being used as a strong electrolyte. And once again, we see our lead going from 0 to +2 in this particular case. And on this side here, our lead going from +4 to +2 in this case. And getting now, this is a lithium solid state battery, and it has, as the anode, sort of a conducting carbon material, like graphite. It has little holes in it that allows, really, as this guy gets oxidized over here in our anode compartment, to travel across to the other side as well. And it can be recharged hundreds of times It's a very light metal, which is why sometimes they use obviously lithium batteries for a lot of purposes. You don't want a really heavy battery in things, so it makes it a little bit lighter along the way. And again, can be recharged a lot because of some solids that you sort of get as a result of reaction that occurs here. Another type of battery, which is not necessarily a traditional sort of battery, is a fuel cell. And a fuel cell requires really a continuous supply of, in this case, hydrogen and oxygen. This is what they wanted to make sort of cars into using a hydrogen sort of fuel cell or hydrogen car. We obviously have sort of want more batteries these days, but you need sort of a injection there of hydrogen and oxygen in there. And one of the ideas behind this is that the overall reaction basically produces just water to get pollution and stuff like that. That's why they want to do that. Here we see the hydrogen going from 0 to +1, again getting oxidized. Oxygen going from 0 to -2, again getting reduced. Uh, Obviously, like I said before, we kind of moved on to sort of hybrids, and definitely. So again, not really responsible for any specific sort of batteries or anything like that, but you do need to know generally how a battery is kind of similar to a galvanic cell and some differences. Corrosion as well is something else we're going to talk about. So corrosion is really returning their metals to their natural state. For all intents and purposes, corrosion basically is the oxidation of metals. So a fifth of steel is produced to replace rusted metals. All metals that have an SRP value, which is that standard reduction potential, which you find in that table, you look up those E values, that is less positive than oxygen, is susceptible to corrosion. And that is because the metal that is less positive. As we know, when we build a galvanic cell, essentially, the one that has the more positive SRP will be the cathode. In that situation, would put oxygen as your cathode. That would then put your metal as your anode, and it's going to get oxidized and go through corrosion, basically. And you will get a spontaneous reaction in that sense with the oxygen having a more positive SRP value. Now, not all corrosion is necessarily really a bad thing or anything like that. Sometimes corrosion can actually protect the metal that's underneath. So, for example, what happens sometimes is when a metal kind of goes through corrosion, kind of builds a corrosive layer up on top. And if that corrosive layer kind of sticks around, it will have to protect the rest of the metal that's underneath it from further corrosion and exposure, obviously, to oxygen. For example, here, aluminum oxide will inhibit further corrosion. It will form a layer that will be on. Problem is when you do that with iron and you make rust, uh, rust falls off. And rust falls off and exposes fresh new metal underneath it. You continue to get corrosiveness and go through further. Copper also, for example, forms a nice greenish, sometimes expensive patina type of look, right, when it goes through corrosion. Silver will tarnish and form silver sulfide. Gold, with an SRP value that is larger than oxygen, will not go through any corrosion. And again, that's because of that situation. When you put oxygen up against gold, gold's going to be a more positive SRP value, which means the gold in that situation will be the cathode and the oxygen would be the anode. Thus, obviously, gold would not go through any type of oxidation or corrosion in this case. Now, when we talk about rust, you basically need three things for rust to form. You basically need a little bit of iron, a little bit of moisture, and some oxygen. And those are all the things that are essential for basically rust to form. Rust basically forms through the oxidation of iron twice, actually. Iron will become iron 2 through this reaction here. And the iron 2 will travel down where it then become iron 3. hook up with the oxygen and form iron 3 oxide. Again, the problem with obviously rust, as I mentioned, is it typically will fall off and expose new metal to it. Why it happens a lot with steel is there's little pits in steel, and these are great areas for moisture basically to sit. And now you got pretty much all the components you need, iron, oxygen, and some moisture for basically rust in this situation. Ending up costing lots of money. Now, there are ways to prevent corrosion and a couple different ways that you can prevent corrosion. You can do something like add some type of paint or metal plating, right? So they sell what is called Rust-Oleum paint, right, to provide a protection layer. Chromium tin can be used to plate steel. They oxidize and they will form sort of a protective cover. Galvanizing as well will also sort of perform a protective cover. And that's because when you kind of put iron and then you cover it there with some zinc between the two in this situation, now iron actually is more positive than the zinc. So all the bad stuff will happen at the zinc parts rather than the iron in this case. So the zinc would go through basically oxidation before the iron, which is the main part probably of whatever you're trying to protect in that case. And in this case that says there, it acts sort of as a sacrificial sort of coating where all the bad stuff can happen there again. The metal that you want there. Alloying is another way to prevent corrosion. And again, in this situation, something like stainless steel contains chromium and nickel, and they form these oxide coatings that changes basically the SRP value of that stainless steel into a noble metal, which means it will be more positive in oxygen and not go through corrosion. Now, another sort of way that you can kind of protect corrosion is cathodic protection. You could do something like magnesium that's connected to a pipeline or a tank that's maybe buried underneath the ground. Magnesium is a better reducing agent than iron. Remember that things that are reducing agent get oxidized. So if magnesium is a better reducing agent than iron, it's going to oxidize versus iron, and thus it will kind of the same idea, alter down on magnesium and protecting your iron tank that you buried underneath the ground. Probably don't want to dig it up every couple of years. Fix it here again. Now all the oxidation is going to occur over here and not over here. And again, that's going to allow the plus 2 now are reduction. So for batteries, like I said before, you just need to know how it's similar and different to a traditional galvanic cell. Corrosion, you just know maybe a few ways to prevent it. That's probably the question. But, but last thing we're going to talk about in this chapter is electrolysis. And electrolysis is the process where we use electrical energy to cause a non-spontaneous reaction basically to occur. And you can think of, I guess, electrolysis as like the opposite sort of process of putting something together. So if you take a battery or something like that to provide some extra current and power there, that will cause our electrolysis to occur. So if you had something like sodium chloride, you could break it apart into sodium and chlorine. Probably. And what happens in this particular case is our anode is actually the chloride, and the cathode is actually the sodium. It is different than when you put it together to make sodium chloride. And so just so we follow that, if I were to make sodium chloride, I'm going to take some sodium and some chlorine and make some chloride. That's two there. In this case, the sodium is going from 0 to +1, and the chlorine is going from 0 to -1. So when you make sodium chloride, it is the sodium like we expect, since it's the metal that's going to be our anode. And it is the chlorine gas here that is going to be our cathode to get reduced. When you're rolling in the other direction there, the sodium chloride here is starting at +1 and ending at 0. The chloride starting at -1 and ending at 0 in this case. So going through electrolysis, when you break this up, the sodium is going from +1 to 0, which means it is actually getting reduced, and it is the cathode, while the chloride here is going from -1 to 0, becoming more positive, and it is getting oxidized, and it is the anode. And that is what you see in this picture. In an electrolysis cell, it is the chloride that's actually the anode because it is getting oxidized, and it is the sodium ion that is actually getting reduced in this case. So oftentimes when people have to do or write an electrolysis sort of half reactions, they always sort of do it backwards because they always think about it as like the making of it as we make sodium chloride. But again, in this case, we're kind of breaking it back up into an element. So what normally is your anode, water is another example of electrolysis that you can do. Take water, take a little bath, yeah, yeah. Uh, Usually you have to make the water help out with some H plus ions floating around in the solution. And with that being said, when you read questions that involve electrolysis of water, very often they will not say water. They'll talk about electrolysis cell that has something to do with like dilute sulfuric acid or some type of acid. So a lot of times they won't just straight up say water. They'll say something about an acid, and that's usually an indication that it is the water electrolysis that's going on. In this case, we're essentially going to take our water and break it back into hydrogen gas and oxygen gas. And we'll do a 2 there and a 2 there. Once again, in this situation, it is opposite of how we put it together. The hydrogen in this case is +1. The hydrogen over here is 0. So in this particular case, our hydrogen is actually getting more negative, and it is the hydrogen that is getting reduced in this case. And it would be our cathode in our electrolysis cell. The oxygen here is going from -2 to 0, so once again becoming more positive. So it's the oxide in this case that is going through oxidation and would be our anode in this particular case. So once again, it's a very common error when people are doing electrolysis. They really kind of get things backwards because, they kind of think of it as putting it together. So here's an example of electrolysis running some current through it, and you can see the bubbles. That's your hydrogen gas and your oxygen gas. And then obviously in these test tubes had water, and the water got displaced by the gas. So in the empty spot here in the test tubes is the hydrogen gas and the oxygen gas in that case. And why do I have more hydrogen and oxygen? Because it's H. The hydrogen and oxygen, so you get twice the amount there of hydrogen gas that comes off as you do oxygen gas. Now, when we're running electrolysis cell, we can do some calculations that involve electrolysis, and usually it's sort of a pretty stepwise fashion that we sort of do this. You usually go one of two ways, either from the top to the bottom or from the bottom to the top in this case. So a lot of times you are given the current at which the cell is running, the amperage, and how long you run the cell for. Now, a amperage is equal to a coulomb divided by a second, and that is that relationship right there. So that's an important sort of relationship. So what we typically do is we take the current and how long we're running the cell for, we kind of convert the time into seconds, and we multiply those together, and we end up with the charge in coulombs. Then we divide the charge in coulombs by our friend, basically Faraday's constant, that 96,500 number that we saw previously. So we divide it by 96,500 coulombs per mole of electrons. And we end up with basically how many moles of electrons we got going on. Now, this is where the half reactions come into place for your anode or your cathode part of your electrolysis cell. In your half reactions, you will have something like a metal and maybe like 2 electrons or something like that. And you will use the half reaction to figure out the moles of electron to the moles of whatever you're interested in, be it, say, sodium, be it calcium, be it whatever it may be. And you will use that as sort of stoichiometry to get the moles of, say, the element. Once you have the moles of the element, there's basically two things that typically you kind of finish out the problem with. One thing is if you're interested in how many grams you would produce or something like that, you would use the molar mass and convert the moles into grams. So a very common ending to these problems is take the moles and use the molar mass from the periodic table and get some grams. Another very common sort of ending to this is much like we just saw with the water in that picture, we did not produce a solid, but we did produce gas. And a lot of times what we're interested in is how much volume of gas we would produce in the cell if we just let it run. So gases involve usually our favorite gas equation ever, PV equals nRT. So in these type of problems, if you're given a temperature, you're given a pressure, and you could use this here to get to the moles, and obviously R is a constant, you could solve for volume, which would be nRT over P. And again, that's a very common sort of ending, especially again, if you're collecting some type of gas in this situation. A reminder that you want to make sure that everybody's in the correct units here. So pressure, when you use the ideal gas law, again, should be atmospheres. Volume you typically solve for is liters. N should be moles. R is the 0.08206 number, or 0.0821, whichever one you like. And obviously our temperature does need to be in Kelvin in this case. So again, like I said, that's a very common sort of ending to these problems. The other sort of version of this problem is they tell you how much you collected, and you kind of work backwards going in the other direction and try to figure out maybe how long you ran the cell for, or what the amperage was or the current was in the particular cell. So those are, two very common sort of ways. A reminder as well, since we're talking about gases, right? 1 atmosphere, 760 torr, 760 millimeters of mercury, right? Hopefully. All right, so let's take a look at one here together. We'll come back to this one, I think. All right, so let's say we want to know how much calcium we will produce in an electrolysis cell when we start with some molten calcium chloride. If the current is 0.452 amperage is passed through it for 1.5 hours. So when we're doing this, remember we're starting with this guy here, our calcium chloride, and we are going to break it apart into calcium and chlorine here. And that is what is going on. And in this case, we have +2 to 0. So once again here, this is getting reduced, the calcium. And we're going from -1 to 0, which means, again, the chloride here is getting oxidized in this case. And if that means that, as I mentioned, the chloride would be our anode, and the cathode here would be our calcium in this particular case. All right, so let's take the information here. So first off, our 0.452 amperage is the same thing as 0.52 coulombs per second, as once again, an amperage is equal to a coulomb per second. Since my unit of time there is in seconds, I may want to convert my hours into seconds just to make everything nice and easy. 1 hour is about 3,600 seconds. So that's going to be 1.5 times 3,600. It's going to be 5,400 seconds. Now that I have really those two pieces of information in the correct units, I'm going to take the time I ran the cell for in seconds. I'm going to multiply it by really the current and the amperage there that I was running it for. And if I do that again, the seconds are going to cancel out. And we're going to end up with 5,400 times 0.452, 2440.8 coulombs. At this point, like I mentioned on the last slide, this is typically where we then would use Faraday's constant to get us from coulombs to moles of electrons. So it is the same number we used previously. In this case, that's 96,500 coulombs per mole of electron. And again, that basically is Faraday's constant in this case. And that is going to get rid of our coulombs and leave us basically moles of electrons. And we're going to divide it by 96,500. That's going to get us something like 0.025, I'll call it 3 moles of electrons. Question. I would say this is a pretty standard sort of start to these type of questions. Again, the goal here is really to get to moles of electrons. And the reason we want to get to moles of electrons is now we could actually use our half reactions to figure out how much we're going to actually produce. So in this particular problem, we're actually interested in calcium, which is our anode. And from the half reaction, we can see that we have moles of electrons, and that is chloride. So we'll come down here. Calcium is our cathode. 2 moles of electrons there as well gives us 1 mole of calcium. So for every 2 moles of electrons, I get 1 mole of calcium. We're really just going to use that as a conversion factor to get us to moles of calcium, 0.025 moles of electrons. Again, opposites cancel, so 2 moles of electrons on the bottom, 1 mole of calcium up on top. And we're going to end up with 0.01265 moles of calcium. At this point, like I said before, since we are interested in grams, we could go to the periodic table and get the molar mass of calcium, which should be 4008 if you look it up there. So using the molar mass of calcium, 4008 grams per mole, that is going to get rid of our moles, and that will tell us how many grams of calcium we will produce in this case. And that's going to be a whopping 0.51 grams of calcium will come off in this case. Any questions on that there? Now, if we want to know how much chlorine gas we would produce in grams, we could do the same calculation. We could just go to the anode half reaction and do the moles of electrons to the moles of chlorine. If we actually were given some temperature values and maybe some pressure values, we could have used the ideal gas law to figure out the volume for something like chlorine gas that we would have maybe produced as well. Any questions on those steps there? All right, so I tried one. Why don't you try one here? Why don't we go back and take a look at the one we skipped? So we are going to run a current of 1.26 amperage and is passed through an electrolysis cell that contains sulfuric acid. We're going to run it for 7.44 hours. We want to know what is the volume of each gas that is generated at STP. So as I mentioned earlier, it doesn't mention anything about water in this one, but this is the electrolysis of water. So again, that's kind of the key to kind of know. They're talking about the electrolysis of water. Like I said, a lot of times they just won't come straight out and tell you, it's the electrolysis of water. They'll tell you something about the acid solution. So we will use those half reactions here. So you don't have to rewrite them. We'll put them here. I'll put the information here, 1.26 amperage, and we're running for what, 7.44 hours. And we're at STP. STP is standard temperature and pressure. That means the pressure is 1 atmosphere and the temperature is 273 Kelvin. Yeah. All right. So take a few moments. We're looking for the volume of oxygen gas and the volume of hydrogen gas in this case. See what you come up with. Okay, so let's take a look, see how you're doing. So once again, I'm just going to kind of start the same way since we're given basically the amperage and we're also given the time the cell was run. We just, again, want to sort of get them in the right units so that we could kind of end up with our coulomb there. So again, because an amperage is equal to a coulomb per second, we basically could just swap the units on that one. And obviously here we probably want to convert our hours into seconds. So an hour, 3,600 seconds. That's going to get us here 7.44 times 3,600. That's going to get us about 26,784 seconds. And again, we can use that now with our kind of correct units there. So we can kind of see how things are going to cancel of our amperage. Again, multiplying those will give us our coulombs of charge. And that is going to get us, looks like 3,374.7.84 coulomb. Again, at this point, really the goal is to get to moles of electrons. So this is where we use our Faraday's constant, and we're going to divide by it so that we do end up with moles of electrons here. And again, the coulombs here will cancel. So we'll divide by 96,500. And that's going to get us a 0.3497 moles of electrons. Any questions so far? All right, at this point, we do want to get the moles. And then since we're interested in really both gases, we might as well just get the moles of both gases here up front. And we can do that now that we have the moles of electrons. So looking at our anode here, which is our hydrogen, our oxygen, in this case, we could look at the relationship between oxygen and moles of electrons and moles of oxygen in this case. We see from the equation there, the half reaction, we have 1 mole of oxygen gives us 4 moles of electrons. So using our moles of electrons we just calculated, we're now going to basically turn those into moles of oxygen. And it looks like it is, again, 1 mole of oxygen, 4 moles of electrons. And that's going to get us here about 0.08743 moles of oxygen. We could do the exact same thing here, but look at our hydrogen in this case. And if we look down here, we can see there is a 4 on the outside, which does get multiplied in. So that would give us 4 moles of electrons, and 4 times a half is 2 moles of hydrogen in this case. So we would have 2 moles of hydrogen, gives us 4 moles of electrons. If you want, you could also reduce that down to 1 to 2 as well. It comes out obviously the same. We are going to start once again with our moles of electrons. We're going to use that relationship from the half reaction to get to moles of hydrogen. And again, in this case, I'll use the number that was there. So 2 plus U and 4 moles of electrons. Like I said, you can do 1/2 as well. So we'll take that. And that's going to get us 0.17486 moles of hydrogen. Now that I have the moles of hydrogen and I have the moles of oxygen in this particular case, once again, we are looking for the volume and it is a gas. So a little PV equals nRT action would be probably good. And we do have the temperature and the pressure given to us because it is at STP. R obviously is a constant, and we just calculated N for each of the gases. So we pretty much have everything we need to solve for the volume of each of these gases. So we'll go back to oxygen here. And the volume of oxygen would be nRT over P. Popping in our numbers here, our moles of oxygen, 0.08743. Our gas constant, 0.08206. And our temperature, 273 Kelvin, all divided by 1 atmosphere in this case. Everything's going to cancel. Moles will cancel. Kelvin will cancel. Atmospheres will cancel. Going to leave us liters as our answer there. And we will end up with, might want to use the right number, would be good. We'll take that one times 0.08206 times the 273. Get us about a 1.96 liters of oxygen would be collected in this case. We then could basically just do the exact same calculation for hydrogen. The only difference is obviously here we would use hydrogen's moles. So the volume of hydrogen would be, again, our N for our hydrogen, which was 0.17486. Our R, 0.08206. Our temperature, 273 Kelvin. Again, all divided by 1 atmosphere in this case. And we'll go 0.17486 times 0.08206 times the 273. That is 3.92 liters of hydrogen was collected in this case. First off, any questions on that there? By the way, we could also solve this without the ideal gas law, as you might remember from the previous class, because this is at STP. At STP, 1 mole of any gas equals 22.414 liters. So you could actually use that conversion. So you could have took any one of these moles, basically, 0.17486 moles, and did a mole is 22.414 liters. You get the same thing if you wanted to do that without using the ideal gas law. A reminder that you can only use that number if it is at STP. You cannot use that conversion of 1 mole equals 22.414 liters if it is not at STP. So it's got to be at STP in this case. Any questions on that there? If I take the volume of hydrogen divided by the volume of oxygen, I end up with 2. Yes, so twice the amount. Yeah, there in that case. Question on electrolysis sort of calculations. Like I said before, the sort of alternative this is, they tell you how much you produce, you work backwards, like I said, and kind of solve for one of those things, the current or how long you ran the cell for. Any questions on that there? All right, that wraps up this chapter, believe it or not. All right, so we are off to the next chapter, which is chapter 18 and nuclear chemistry. So we'll talk about nuclear chemistry here. So nuclear chemistry involves radioactivity, and a radioactive nuclei will spontaneously basically decompose into a smaller nuclei. That is what is sometimes referred to as radioactive decay. This can happen sort of spontaneously by itself. This could also happen if you kind of agitate somebody and then make them go through that and kind of help them along. Now, typically what happens in a nuclear decay situation is Involves usually emitting some type of particle and usually energy involved in it. Usually the parent nuclei, the nuclei is sometimes what we refer to as like the nucleus, and the sort of isotope that's undergoing this sort of process is the one that is going through radioactive decay. The daughter nuclei is the one that is going to be made as a result of it, which is the new nucleus. One of the major differences between nuclear reactions and chemical reactions, which is what we normally talk about, is we actually do not have conservation of the elements. So we start with one element and we make different ones. And that's very different than chemical equations and chemical reactions, where if you start with like 4 carbons, you'll end with 4 carbons. And here, again, it's very different in this type of situation. Anything on the periodic table there, 84 or above, typically it's going to be radioactive. A lot of the radioactive ones there on the bottom of the periodic table. Also the ones with the fun names, the made-up names, and all those things, the made-up elements, like Einsteinium, Nobelium, all those kind of guys down there, Berkelium. Now, when we talk about radioactive decay, there are different types of particles that we come across. And our good friend Rutherford discovered 3 types of particles. We remember Rutherford. He did an experiment with some gold foil and all that good stuff, and he shot alpha particles at it. Oh my. So let's talk about those things. So alpha particles are basically radioactive particles, and they are symbolized one of 2 ways in nuclear chemistry. They are symbolized with the alpha symbol with a 4 and a 2. Or really what an alpha particle is the helium nucleus. So they are also symbolized with helium here. There I asked, the top number is what number? I heard somebody say mass number, because I would agree with you if that's what you said. Bottom number is, got a little quieter there. That is the atomic number there. A little throwback day today. Mass number is protons plus neutrons. Atomic number is protons, yeah. Can I find both of them on the periodic table? No. Which one can I find on the periodic table? I can find the atomic number on the periodic table. That's the atomic number right there. By the way, on the bottom is not the mass number. That is the atomic mass, which is different than the mass number. Mass number, atomic number, protons, electrons, neutrons, they all should be positive whole numbers for sure. All right, so those are 2 common sort of symbols that we see. Beta particles also symbolized with 2 different sort of symbols. They will use the beta symbol and a 0 and a -1, or they will use just an E for an electron, because, it's basically an electron here, and they'll use that. Gamma rays are just pure energy. Maybe you remember electromagnetic spectrum. You find the gamma rays right at the end. Short wavelengths, very high in energy. It uses the symbol gamma and usually 0 and 0. In addition, there's other types of particles we'll come across. We have positrons, which are like electrons, but with a much better attitude, because they're very positive. Thank you for not laughing. I appreciate it there. Also uses the same symbols as the beta particles. Now, how do you know it's a beta particle versus the other? I would say you are probably pretty safe to assume it's a beta particle if you just see the beta symbol. Usually if it's the positron, they will put something with a positive there. So like if it's a positron, they usually like maybe even put the positive up there or something like that. So they usually will indicate that it is the positron, if they're kind of using the same symbols for sure. We will also talk about a process that's known as electron capture. There it is. So again, our atomic number is on the bottom left of our symbols. And again, it tells us the number of protons. A reminder that the atomic number does really only tell you the number of protons. It will also tell you the number of electrons if the thing is neutral. But if it is not neutral, then obviously you will have different numbers of electrons. And the proper definition of atomic number is just the number of protons. So speaking of protons, that also is a symbol that we see a lot in nuclear chemistry. And much like most of them, there's a couple of symbols that are typically used. A P to represent a proton with 1 and 1, or hydrogen, 1 and 1. By the way, to figure out the number of neutrons, right, we take our mass number and we subtract it from our atomic number. R in this form, top number minus bottom number, basically, right? A neutron is also something we see a lot in nuclear chemistry, and that is the symbol for a neutron. It is an N with a 1 and a 0. Obviously, our electron, our beta particle, really, our positron, and again, our alpha particle there are a couple of symbols. So again, kind of interchangeable. They do kind of float around between symbols a lot here. Now, depending on what type of emitter that this radioactive particle may be, or this thing going through radioactive decay may emit, it can provide, or you do need maybe different layers of protection. So for example, an alpha particle, will basically go through, you just need like 0.01 millimeters of lead. Beta will penetrate a little further, and gamma, that is penetrating all day. So if you ever work with anything that is radioactive, you should always find out what type of emitter it is, and that should usually dictate what type of safety equipment that you need. Sometimes all you need is gloves, and sometimes you need gloves, lab coat, distance, and a lot of lead and barriers between you and whatever's emitting. Here are a few other sort of symbols in case you didn't like the first 3 ones that we looked at there. Let's talk about balancing nuclear equations, which is super difficult and really hard for people to grasp, but I'm just kidding. You actually just need to add. It's pretty straightforward in this case. So to balance nuclear equations, because we do not have conservation of elements, it is different than how we balance a chemical reaction or equation. Because in a chemical equation, if we again start with 4 carbons, we will end up with 4 carbons on the other side. Here, we do not have the same elements on each side. So when we go to balance a nuclear equation, there's really kind of 2 things that you basically have to make sure of. And that is when you add up all of the mass numbers on the left-hand side for everybody, in this case, you get like a 236. It needs to equal all the mass numbers on the right-hand side. So you add up all that, 138, 96. By the way, that 2 does get multiplied here. So that is another 2 there, which will give you 236 in this case. So if you do have a coefficient in front of like a neutron, you do have to kind of count the numbers, however many you got going on. And the other way that we balance it is basically we just need to make sure all the atomic numbers on the bottom match each other. So if we look at the atomic numbers here on the bottom, that's 92 and 0, which is 92. That's 55, 37, and 0, also 92. So to balance a nuclear equation, you basically just need to make sure all the mass numbers equal each other on both sides and all the atomic numbers. So how will you typically see this? One of 2 ways. You will either be given an equation such as this, and something would be missing. And that's a very common sort of question. And basically, the idea here is because the atomic number is the most important thing, right? And that is because everybody on the periodic table has a different atomic number because they have different numbers of protons. And out of protons, electrons, and neutrons, it is the proton that determines what element you're dealing with. That is also, by the way, why we do not have conservation of elements, because in chemical reactions, it's all about making and breaking bonds, which involve electrons. Nuclear reactions is all about everything in the nucleus, protons, neutrons, and changing those. So that's why we do change elements in nuclear reactions versus, say, chemical reactions. So since the atomic number tells us kind of what would be missing, we would want to add up our atomic number on the left and come over here and go, all right, that's a 55, and that is a 0. So I got 55 going on here. I subtract those two, that's going to tell me 37. Then I should travel over to my local periodic table and look up number 37 there, atomic number, and you will see the symbol of what is missing, right? And now I know, hey, that is this guy, and that's a 37. For the mass number, we do the same thing. We got 236 up on top, and we're going to subtract it from 138 and subtract it from 2, and that's going to give us our missing mass number, which is on top, and that obviously is a 96 in this particular example. So if there's something missing, periodic table is your best friend on this deal. You want to figure out the missing atomic number, and that will give you what element's missing. Now, mind you, you could possibly have a particle missing. So if you do that and it doesn't really match anything on the periodic table, in terms of the atomic number, it may be some type of particle, like an alpha particle, which might match, or a neutron or something of that nature. The other way that we have these type of reactions is they will tell you, hey, we'll just borrow this guy, uranium 236 is going through a alpha decay. And basically that's all they'll kind of tell you. And there's kind of two sort of words to think about. If something goes through an alpha decay or a beta decay, or it emits an alpha particle or it emits a beta particle, what that basically means is that particle should end up on the product side. So if it goes through that type of decay, or again, it says something like it emits a beta particle, alpha particle, whatever it may be, that particle should end up on the product side. Obviously, what you're starting with should start on the reactant side, and then you can kind of build your equation of what's missing by the missing atomic number to balance it out. The other sort of words that you sometimes hear is you bombarded something, like you bombarded something with some neutrons. If you bombarded something like with a neutron, that ends up on the reactant side. Or if you do an electron capture, that ends up on the reactant side. So those are the common sort of words that you sometimes hear in these type of problems. Anything that's like an electron capture, anything that you bombarded something, that particle should end up on the reactant side, probably with whatever you shot it at. And if it sort of goes through this type of decay, that's probably going to emit that particle on the product side. And again, at that point, you probably will have just whatever is left over to balance it out, the mass number and the atomic number, and you can figure it out at that point. Any questions?